For our second set of notes for the day and our final set of notes for this unit, we're looking at the basic counting rules. And this really should be pretty straightforward. I know that when we looked at the Bayes rule, there was formulas that you had to look at, and you had to know how to substitute things in. With the counting principles and the counting rules we're going to look at, this should be some stuff that you've actually seen probably even in middle school and maybe encountered on the ACT. So the basic counting rule is the first thing we want to look at. And it's really, it's also sometimes called the multiplication counting principle. And with the basic counting rule, we're going to just use an example, I think, rather than read through all this and talk about how many different ways an event can occur. So with example 1, we have the Robson Communities builds new home communities in several parts of the western U.S. In one subdivision, they offer 4 models: the Shalimar, the Palacia, the Valencia, and the Monterey, each in 3 different elevations. So those are designated A, B, and C. How many choices are there for the selection of a home, including both model and elevation? So what I'm going to do for illustrative purposes is we will just use the first letter of each one of these models, so S, V, and M, and I'm going to list these in a column. So we have S, V, I'll skip P, sorry, S, P, V, and M. And then each one of these is offered in 3 different elevations, A, B, and C. And that applies to all 4 of your choices. So basically you can make this tree diagram to kind of come up with the numbers. And you can see that, so the Shalimar, you have Shalimar A, Shalimar B, Shalimar C. You have Palacia A, Palacia B, Palacia C, and so on. You can make this tree model every time if you wanted to, but you can actually see that it's just simply the number of choices in this column times the number of individual choices in this column. So in this case, it just ends up being 4 times 3, which is 12. So there's 12 different choices for a selection of a home. The reason you want to avoid making a tree diagram like this every single time is when you get into much larger factors that you want to consider, such as maybe something really, even something that does seem simple, such as picking out an outfit. If you have 6 pairs of jeans, 7 shirts, 3 pairs of shoes that you want to consider for an outfit, you don't want to make a tree diagram for all 6 pairs of jeans with all 7 shirts matched up to all 6 pairs of jeans, and then with 3 pairs of shoes matched up to each one of those shirts. It's much easier to use the multiplication counting principle, where you just multiply the number of items in each category to come up with the total. So like if you were looking at pizzas, for example, how many different toppings do you have that can lead you to know how many different types of pizzas you can create. So when we talk about the basic counting principle or basic counting rule, like I said before, it's also considered as the multiplication counting principle. You just simply multiply the numbers together that you're looking at. So right here is a summary of what we just looked at with example 1. It's the number of options in the first model times the number of options for the second model or option or choice that you may have. So 4 times 3 is 12. And it's really easy to do that using the tree, or it's also even easier to do that with using the multiplication counting principle. So example 2, we're talking about license plates. So the license plates in Kentucky traditionally consist of 3 letters followed by 3 digits. Part A, how many different license plates are possible? And part B, how many license plates are possible where no letter or digit is repeated? So now we're going to look at something a little bit different. First, let's look at part A. So let's think about a license plate. We have 6 spaces in this license plate, 3 letters, 3 digits, and we're talking about they can be repeated. So we could have AAA000. That is a valid license plate. But for each of the 3 letters, so that's our first 3 right here. So we have 3 letters. And then here we have 3 digits. So there are 26 letters in the alphabet. So we have 26 choices for that first position. Again, we have 26 choices for the second position. and 26 for the third. Then when we move over to the digits consist of the numbers 0 through 9. So we have 10 choices for the first position, 10 for the second, 10 for the third. What's nice about this, we just multiply all these together and we come up with the number 17,576,000. So considering that we can have repeated digits or repeated letters, there are 17,576,000 possible unique license plates that you could have in the state of Kentucky. This is a perfect example where you do not want to have a tree diagram, because you'd have 26, and then with that 26, you'd have 26 coming off of that, and then 26 coming off of that, and then 10, 10, and 10. And that's going to be 17,576,000 branches at the very end. Now, what's different about Part B is that it says it has a stipulation on it where no letter or digit is repeated. So the difference in this one is we cannot have AAA000. We have to consider a new scenario. So again, I'll make out the 6 positions. Again, the first 3 are the letters, and the last 3 are the digits. So for our first 3, where the letters are at, again, for the first letter choice, we can choose A through Z. So there's 26 possibilities. But once we choose a letter out of that, we cannot have that letter repeat again. So that leaves us with 25 letters for the next position. And then once again, this letter cannot be repeated. So we have 24 letters to choose from for the third position in the letters section. Then we move over to the digits. It's going to be the same scenario. It's 10, then 9, and then 8. And so when we multiply those together, we get much fewer license plate possibilities. We actually end up with 11,232,000 possible license plates. And this is going to give us a new, Part B introduces a new number technique that some of you may have heard of or may have seen before, called a factorial. And a factorial is just, you simply take, if you're given, say, 3 factorial, if you see that in a factorial, I'm just going to go down to the notes here and not try to write it out. A factorial is written as a number, some integer, with an exclamation point. And what it means is you take each number, starting with whatever, in this case, say it was 5, don't mean to use the highlighter, say you had 5 factorial. What that means is 5 times 4 times 3 times 2 times 1. You can ignore the times 1 because that's redundant. You multiply anything by 1, you still get the same value. So 5 factorial is 5 times 4, which is 20, times 3, which is 60, times 2, which is going to be 120. So 5 factorial has a value of 120. And you can see that going on up here in our previous example, where the digits did not repeat and the letters did not repeat. It's 26 times 25 times 24. If we had 26 slots on the license plate, it would continue on to times 23, times 22, and so on. So a factorial is not really anything new. It's just a new notation maybe to some of you. But we just want to determine an example 2, 3 factorial, 4 factorial, and 5 factorial. So 3 factorial is 3 times 2 times 1, which we know to be 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. 5 factorial is 5 times 4 times 3 times 2 times 1, which we already calculated to be 120. 6 factorial will be 720, and we could keep going on. With example 3, we are talking about a collection of objects that are consisting of the letters A, B, C, D, and E. And we want to list all possible combinations, or list all possible permutations of the 3 letters from this collection of 5 letters. So what's different here is we're talking about something called a permutation. And let's see, I thought I mentioned that. I did not. All right, so the permutations is the way that we can arrange things, okay? So if we take the letters A, B, C, D, and E, we're talking about a permutation is the different ways that we can arrange them. So for Part A, it says list all possible permutations of 3 letters from this collection of 5 letters. So we're only picking 3 letters out of the 5, and we're looking at all the different ways they can possibly be arranged. Part B says use Part A to determine the number of possible permutations of 3 letters that can be formed from the collection of 5 letters. That is, find 5 permute 3. So that means we have 5 total objects. We're looking at how many different ways we can arrange them in threes, in groups of 3. And then we're going to use the basic counting rule to determine the number of possible permutations of 3 letters that can be formed from the collection of 5 letters. So that is going to be just to find 5 permute 3 by using the basic counting rule. And as I said right here, because I'm not some diabolical tyrant, I'm going to save us some time and present the solution to Part A. You can see right here that's a lot of different permutations. We have ABC, ABD, ABE. Then we jump and we drop the B, and now we have ACD, ACE. So when you do these on your own, be very methodical. There's a lot of permutations here when you have 5 objects, and we're just looking at ways to rearrange them in 3 different ways. So we just want to consider, just for right now, that we have this set right here. I'm going to pause the video for a minute because I need to pull up my calculator to show you something else real fast. Okay, so now we're back. We're on Desmos, and we're just going to use the calculator to do the permutation count for us rather than count all the individual items in that list. What you can do in Desmos is to find out how many different ways can you arrange 3 items out of a possible choice of 5. You're going to go to Functions, and you're going to select Stats from this menu. And then down here, these are the 2 that we're going to be looking at the most right now. We have NCR and NPR. NCR is combinations. How many different groups can we create of 3? Permutations is how many different groups of 3 can we arrange in unique order. So we're talking about permutations right now. So you just click on NPR, and we're talking about 5 objects with, I wish I would stop, in groups of 3. And you can see right here, it already gives us the value is 60. So there are 60 ways that we can arrange 3 objects out of a possible group of 5. And that is kind of borne out by our chart that we see right here. We have 6 in each column, and we have 10 columns. 10 times 6 is 60. And so that gives us the permutation rule. Permutation rule is the number of objects, that's the numerator. It's that number of objects factorial over the number of objects minus the number of ways we want to arrange them factorial. So let's look at that previous example using this notation and doing a hand calculation. So what we were looking for is 5 permute 3. And so that would be 5 factorial over 5 minus 3 factorial. And we end up with 5 factorial over 2 factorial. 5 factorial we've already calculated to be 120. 2 factorial is 2. That reduces to 60. So the hand calculation still, it's fairly quick. But again, the calculator will make life a little bit easier. You can use the NPR for the permutations. We could do the NCR for the combinations. All right, so example 4. We're talking about Keeneland. And in an exacta wager at Keeneland, a bettor picks the 2 horses that they think will finish first and second in a specific order. For a race with 12 entrants, determine the number of possible exacta wagers. We're going to do this one by hand. We're looking for 12 P2. So how many ways can we arrange 2 horses out of 12 possible horses? And when we do that hand calculation, we have 12 factorial over 12 minus 2, close parentheses factorial, which is going to be 12 factorial over 10 factorial. Now, before I go through and I write out 12 times 11 times 10 times 9 and so on, I'm going to show you a shortcut. It's 12 times 11 times 10 factorial, because 10 factorial is 10 times 9 times 8 times 7 and so on, over 10 factorial. What's nice about writing it out this way, the 10 factorials do end up canceling one another, and you have 12 times 11, which is 132. And again, you could check that with the calculator, NPR 12,2, and you should get 132. With our next example, it's another permutation rule. We're talking about a student has 10 books to arrange on a bookcase. How many ways can the 10 books be arranged? So for this one, we're doing all 10 objects across the bookshelf. So if we're not just picking a select few of the books, we're looking at all of the books. So in this case, we're looking at 10 permute 10, which is going to be 10 factorial over 10 minus 10 factorial. And when we reduce that, excuse me, we get 10 factorial over 0 factorial. 0 factorial is just 1. And when we simplify this, 10 factorial is 3,628,800. So there are 3,628,800 different ways to arrange 10 books in a unique pattern on a bookshelf. So that introduces the special permutations rule. You can see that right here. If we're arranging m number of objects using every single object, it's simply just that number of objects factorial. The next thing we want to look at are combinations, and combinations are different from permutations in that, if you recall, let me go back up here to our example of arranging the letters. A, B, C, let's see, where do I have? Trying to find some of the others that are in here. ABC, BCA, CAB, CBA. I haven't found all of them yet, but these are all permutations. When we're talking about combinations, the order that these things are arranged in does not matter. So each one of these is the exact same combination. ABC is no different than BAC or CAB or CBA. Same letters are involved. So we're looking at a different technique here. So the one thing to keep in mind between permutations and combinations is that the order matters in permutations and how they are arranged. In combinations, that order does not matter. I could take a row of desks in my room, and no matter how I arrange them, it's still the same combination. However, if I numbered each one of the desks in my room, and I wanted permutations, then that order is going to make a difference. And I can illustrate that better probably when we're in person together, if that doesn't make a lot of sense. So one more time, we're considering from that previous example that I just went back to, the collection of objects consisting of the 5 letters A, B, C, D, and E. We want to list all possible combinations of 3 letters from the collections of 5 letters. You can see in the table right here, this is a much smaller table than what we had before. And we're going to use part A to determine the number of possible combinations that can be formed. So all we got to do is count this. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's it. There are 10 possible combinations of 3 letters that can be formed. We can use the calculator again. You can go to functions, NCR. I need to delete the permutation there. And here it's going to be 5, 3. And you can see we get 10. So permutations are the number of the number of combinations is going to be much smaller than the number of permutations that you would get out of a given set. And there is also a special formula to come up with combinations, and it involves factorials again. So this part of the combinations rule looks just like the permutations rule, except now we've introduced that R factorial times the parentheses. So when we look at example 7, we're going to apply that using just a hand calculation. New member, we're talking about Redbox, and it's some introductory offer that they have. A new member agrees to rent one movie at regular prices and receives any 4 movies at his or her choice from a collection of 65 movies. How many possibilities does a new member have for a selection of 4 movies? So when we calculate that, this is going to be 65, choose 4. Because it doesn't matter what order they pick the movies in. It's just a matter of that they pick these 4 movies, whatever the 4 movies might be. The order is not important. So what we get using the rule is 65 factorial over 4 factorial times 65 minus 4 factorial. And again, we have 65 times 64 times 63 times 62 times 61 factorial. You'll see why I stopped there. 4 factorial. 65 minus 4 is 61 factorial. So these two, 61 and 61, cancel. And we have 65 times 64 times 63 times 62 over 4 factorial. And 4 factorial we've already calculated to be 24. So let's figure up, pull out my calculator here. 65 times 64 times 63 times 62 is 16,248,960 over 24. Then we divide that by 24, we get 677,040 different combinations of 4 movies that this individual could select out of the 65 possible movies that they have to choose from. Example 8 is another example of using the combinations rule. And in this one, we have an economics professor who's using a new method to teach a junior level course with an enrollment of 42 students. He wants to conduct in-depth interviews to get feedback from these students, but he doesn't want to interview all 42 of them. So he decides to interview a sample of 5 students from the class. So how many different 5 student samples could there possibly be? So let me give it to you this way. Let's just say we have our class, we have Rainey, if I can spell everybody's name right, Rachel, Reagan, oh God, I'm going to spell Reagan's name wrong, I think. Yeah, I think I just spelled that wrong. We have Chelsea, Katie, and Kinley. If I spelled everybody's name right, I am going to go buy a lottery ticket. I have a feeling that I think the one that I messed up on was probably Reagan's. I know she doesn't spell hers the way that I would think. Anyway, let's say I just had you 6 in this class, and I wanted to interview just 2 of you. How many different 2-person combinations can I get? If I just chose, and just for the sake of simplicity, if I chose Rainey and Rachel, Rachel and Rainey is the same combination. So it doesn't matter if I chose Rainey first and Rachel second, or if I chose Rachel first and Rainey second. That's just still one single combination. So what we're looking at with this particular example is 42 students, and we are choosing 5. So in the context of the notation, we have 42 factorial over 5 factorial times 42 minus 5 factorial, which is going to be 42 times 41. Over 5 factorial times 37 factorial. Cancel those. And so I end up with 42 times 41 times 40 times 39 times 38 divided by 5 factorial. Type that in, and we get 850,668. So this professor could interview any one of 850,668 possible samples of 5 students in his class. And there is our combination rule. The number of possible samples of size n I got to learn to pick the highlighter, of size n from a population of size capital N is the combination rule NCN. And then we get into our last example, and this one is one that always kind of throws a few people off from time to time. But we have a quality assurance engineer of a television manufacturer inspects TVs in lots of 100. He selects 5 of the 100 TVs at random and then inspects them thoroughly. Assuming that 6 of the 100 TVs in the current lot are defective, find the probability that exactly 2 of the 5 TVs selected are defective. So what we're looking at here is we have these TVs that are being inspected, and we have 6 that are defective. So that means that we have 94 out of the 100 that are non-defective. And we are looking for me to zoom in a whole lot. There we go. And then so out of the defective, we are looking to find 2 that are defective, and we want to find, since we're sampling 5 TVs, that means we need 3 that are non-defective. So what this is going to happen, or what this is going to happen, I don't even know how to English this morning. What will happen is for the defective TVs, 6 of them we know to be defective out of the 100. We're looking for 2 out of the sample of 5. That can be expressed, just this column is 6, choose 2. Then in the other column where we have the non-defective TVs, we have 94 that are non-defective. Out of the sample of 5, we have to have 3 that are non-defective in the context of this problem. So that's going to give us 94, choose 3. And then what we do with these values is the multiplication counting principle. We take 6, choose 2, times 94, choose 3. And this will give us our probability. Or it'll help generate the values we need for our probability. So 6, choose 2, I've already typed that one in, is 15. And 94, choose 3, again, that's already been typed in, is 134,044. So when I multiply these two numbers together, I get 2,010,660. So now that's how many possible outcomes there are where exactly 2 of the 5 TVs selected are defective. And we need to know how many possible samples there are of 5 TVs. So we have to calculate one more thing. And that other value that we need to calculate is 100, choose 5. How many different ways are there to choose 5 TVs out of the 100? Or how many different combinations of 5 TVs are there out of the 100? So when we set this up, again, it's 100 factorial over 5 factorial times 100 minus 5 factorial. I've already done this one in advance, typed it in. We get 75,287,520. So to find our probability that exactly 2 of the 5 TVs being defective, we're going to take our values that we've computed, the 2,010,660 divided by the 75,287,520. So if we write this out, it's 2,010,660. Whoa, not 666. That's bad. I got to go bless my computer now. 75,287,520. Type that in the calculator, you get approximately 0.027. So there is a 2.7% chance that exactly 2 of the 5 TVs selected will be defective. That's the problem that normally will trip most people up. You just have to be methodical and very careful in how you approach the problem, and then they should make sense. So here is your homework problems for the first one. I know it has J parts to it, but it's just a calculator problem. So you just type in NPR 4,3, NPR 15,4. Just put in whatever your result is. 2, 3, 4, 5, 6, 7. Yeah, there's a few more problems on there. But if you get the handle on how to do these, you will understand this much better, and it will help you in the long run as we continue on throughout this course. Remember, this is our last set of notes for this unit. Test is be on Friday. If you weren't in class today, I did indicate that I will give you a 24-hour window to complete that test. So it will be released at 12 a.m. Friday morning, and I will need it turned in by 12 p.m. Friday evening. That's not to say that the test will be that long. It's just that I want to make sure I give you adequate time to be successful on this first exam, because you will not have that same luxury of having that same amount of time on future exams. I hope you guys are doing great, and I do hope to see more of you on Wednesday. Everybody take care.